today on IODP Expedition 342, Newfoundland.
This is an interval where the world steps out of a greenhouse and into an icehouse when ice sheets first blow up on Antarctica to a big size.
And maybe on Greenland. So we would like to know, right?
That would be news. That would be paleoclimatic heresy, which would make us famous.
If you take the JR, the boat itself, and you add to it all the scientists and the technicians that are on board, you can think of the JR as a true time machine. As you drill down into the ocean bottom, you're drilling back in time. And you bring these cores up onto deck, and you have no idea what time period they came from, but it's the people on board the JR that tell us that story. So we have two teams of people that are basically what I call the keepers of time. So these are the people who actually can figure out where we are in time.
We hope that there are some foraminifera in there that tell us the age of the sediment, so that we can get a good handle of what we really get in our course.
A biostratigrapher is basically a biologist who just looks at biology in past oceans. They not only know all the organisms of their group floating about in the open ocean today, they know that for every single time period for the last 150 million years. It's unbelievable. And so they're the first people that get to the core. The core comes up on deck. They run out to meet this new sediment coming on board the ship. They grab a little bit, and within minutes, they come, running back to tell us, oh, you're back in the Eocene or the Oligocene and the Miocene, where you're looking at changes in glaciation. And so that gives us a first guess of where we are in time. We have the boundary between the Eocene and the Oligocene, and you can tell by looking at the core that we're crossing the boundary in several steps, which is just what we expect and really exciting to see in person.
It's interesting. I mean, what you're seeing here is an artifact of global change that went on in the southern hemisphere, and here we are in the north of land.
We didn't expect this event to show up in this core. If this sample gives us a normal reverse-like sequence, it provides a great typology time. We are very happy.
And the second team, the paleomagnetists, they actually look at which way the North Pole is pointing. And so if you look back in time, the North Pole is flip-flopped, which is kind of incredible, but the magnetic polarity of the Earth itself has changed. And they look at those stripes, and together, the paleomagnetists and the biostratigraphers are keepers of time. So they put us in a single place in time. And when you figure out where you are in time, you actually want to go out and see what was going on in the world. And so that's my job. If you come into the core lab and we're opening one of these cores where we think is around one of these really interesting time period where the world is changing, sometimes you open it up and you miss it. But other times you open it up and you see the world change before your very eyes. And that's super exciting.
Welcome to Titanic Tales. Today we come to you from the Geochemistry Lab on the JOIDES Resolution. 3,500 meters below our feet lies the wreckage of the Titanic. I wouldn't want to sail on this ship. The railings are all covered in slime. Has nobody been cleaning it? Have they taken away the custodial service at the bottom of the ocean? Well, what I can tell you, this coating is composed of iron and manganese oxides. Iron and manganese are among the most abundant elements in the ocean. But there's also communities of bacteria, tiny, tiny communities of bacteria. You can't even see them with your naked eye, but they are enabling chemical processes that would otherwise not be possible. In addition, iron is a critical nutrient in the oceans. Thus, the metal of the Titanic offers more than a heaping spoonful of this dietary requirement for deep-sea microbes. And I've been told it tastes like chicken. In conclusion, although the Titanic has become somewhat of a microbe restaurant, the recycling process that these iron oxide-eating bacteria are involved in are vital to life on Earth itself.
Hello, my name is Heather Barnes and I'm a marine laboratory technician on board the JOIDES Resolution. Today I'd like to give you a brief overview of how we process core for the core lab, from the time we receive it from the rig floor to the final stages of packing the core in the core reefer. It all starts out here on the core receiving platform. The marine laboratory technicians carry the core from the rig floor down here onto the catwalk. And what we do is cut the 9.5 meter length core into 1.5 meter length sections, just for easier handling through the core lab. And from there, we clean it and cap it with clear end caps for the bottom and blue end caps for the top.
Just a little bit gritty. I'm expecting
You want to watch out for those tube worms.
Tube worms, huh?
This is the core entry area, where we enter all of the section lengths that we collected on the catwalk into the database. In addition, we produce labels for every single section on board the ship. This label has a barcode and a specific text ID that allows us to track the sections throughout the core lab and make sure that every piece of data that we collect will get attributed to the correct section. Once the cores have equilibrated, which takes about 4 hours for them to come up to room temperature, the first measurements that are taken on them are the physical properties measurements on the whole round multi-center tracks. We have a track here. You can see the core being pushed through right now. The interval of measurements on these tracks is centimeter scale. So you can just imagine how much data is collected, a lot. So after every section gets run through on the whole round multi-center tracks, we come into the core splitting room. And actually, this is perhaps the most exciting room in the core lab. Just imagine, this section here is the first time it's been exposed in millions of years. And we're the first ones that get to see it in here. So basically, what we do is split every single section into half. A working half and an archive half. The archive half is our permanent record, and our working half is the half that the scientists are allowed to work on. It's the side that they're able to probe and pick at and sample from. You can see here the scientists are actually sampling the cores. The samples that they're taking here may be chemistry samples or further discrete samples for the physical properties laboratory.
I just found the coolest thing in this core. Really? Yeah. I mean, I took a sample, but I don't know where it is. I mean, this is a really important sample.
Should we go find it?
Yeah, we've got to go find it.
Okay, let's go get it.
There he is. Got my sample.
Get him! Sandy, have you seen Charlie Darwinius?
I don't think so. What does he look like?
Well, he's about this big. He has grasping fingers and a prehensile tail.
And he stole my sample.
That's weird, actually, because some of my data on the NGR has been looking really strange today. Maybe he's been around here.
Really?
Well, let's go look for him. And let's look somewhere high with that prehensile tail.
Okay.
Yeah.
Hey, there he is. And my sample.
Charlie Darwinius, get down here.
Hey, Caitlin, you gotta keep an eye on that primate in the lab.
Sorry, he's really curious, just like a scientist.
Hey, speaking of science, let's get back.
Me too.
This here is the archive half section table. This is where the core describers visually describe each and every section.
Yeah, go for it.
Many clays and seal-sized rock fragments.
Once all of the sections are measured in the core lab, they're brought over here and stored in these plastic D-tubes. And then they're brought downstairs to the core reefer where they're stored until port call, where we ship them out to the repositories.
Ocean drilling is just this remarkable feat of technology. I like to go out and just watch how they do it. And so the JR has been instrumental in helping us understand how Earth and life has evolved for over 100 million years. And coming out here, being on the JR, allows me to ask the sort of questions to understand the sorts of futures that we'll be facing.